Alright, so here we go. We are going to go over the answers to the homework. You guys all look very spirited in your spirit wear. But let's talk about phosphorus. So phosphorus has 5 valence electrons around it. Some of them are paired and some are unpaired. The answer would be 2 and 3 for a phosphorus atom, not for bonded phosphorus. For a boring phosphorus atom, it would have 5. 2 of them would be paired up, 3 of them would not be. The normal charge for magnesium is this one here. It's a +2. I am using a mouse, which is why my ability to draw is so limited. The unpaired electrons in an oxygen. So oxygen has 6. Get 2 together, 3, 4, 5, and then the 6th one is paired up. So you have 2 unpaired electrons. Again, there we go, 2 unpaired electrons. And how many are unpaired for nitrogen? -3. I'm going to just borrow the other one. The nitrogen is 1, 2, 3, 4, 5, but it's a -3, so it's got 3 extra. So the nitrogen atom would be 5, but the nitrogen ion is 8, so there are no unpaired. And then similarly, the phosphide ion has 3 extra electrons to fill out the octet. Hey, Mr. Murphy, couldn't I have just said... No, you cannot just say that the configuration for phosphide would be argon. The configuration always shows the valence shell that is outside of the core. So the core electrons would look like neon. The valence would be 3s2, 3p6. I know that that is the same as argon, but it doesn't show any of the valence electrons when you write just argon. Next page. Halogens, alkali metals, and alkali earth metals have how many valence electrons? Pretty simple question. This one here. Yep. Which of the following would gain 2 electrons in order to achieve a noble gas configuration? Gain 2, oxygen, and selenium. So this one here. The electron configuration for sulfur -2. Sulfur has 6. It is 3s2, 3p4. 3s2, 3p4, but that's a -2, so it has 2 extra, so it's actually this one right here. What is the principal quantum number of the electrons that are lost when tungsten forms a cation? Okay, tungsten is 1s2, that's a W, 2, and then it goes for a while, and let's pick it back up when we get close to the end. 6s2, 4f14, 5d, 1, 2, 3, 4, 5d4. So, 1s2, skip a few, 6s2. So what is the principal quantum number, meaning energy level, for the electrons that are lost? It would be 6, because that's the valence. The 6th energy level is the valence. The first 2 electrons for tungsten would come off of here. And then they would come off the 5th, and there's lots of 5s. There's 5 S's and 5 P's that are hiding in this pseudo-ellipse. Which of the following species has the electron configuration argon 3d4? 3d4, I would normally think of it as krypton, but there's no 4s2, right? Wouldn't there usually be argon 4s2? It would normally, but that 4s2 is missing in there, and that means to me that this thing has lost its 2 electrons, and it's probably krypton +2. Here's an example that's kind of similar where they actually put zeros in for the fact that cobalt's lost electrons. Cobalt is a D7. Here it is right here. So this is cobalt having lost its 2 valence electrons. How many single covalent bonds must a silicon atom have to complete a octet? Silicon has 4 valence electrons, so we need 4 single covalent bonds. Has 4, needs 4. Maximum number of double bonds that a carbon can have. Number of double bonds. It can have 2 double bonds. Let's draw this out here. So you got a carbon. Beautiful, nice drawing. And let's change to blue. It's got 1, 2, 3, 4, and then it bonds to some element. And it bonds to some element. Oh, it has to do a double bond to whatever that element is. Oh, it has to do a double bond. So you could have 2 double bonds on a carbon, but you couldn't have a third or a fourth because you're out of valence electrons. Given the electronegativities below, which covalent single bond is the most polar, is the most different? Polar, different. Oxygen and nitrogen, that's a difference of 0.3. Oxygen and carbon, that's a difference of 1. Oxygen and hydrogen, that's a difference of 1.4, 0.9, and 0.4. So it looks like this one, which isn't terribly surprising. That difference between oxygen and hydrogen is what results in the hydrogen bond. That difference between oxygen and hydrogen really sets up a polar bond there that all sorts of things take advantage of. More on that later when we get to intermolecular bonding. So this question is about the trend, but make sure you know what causes the trend. Electronegativity blank from left to right within a period. It increases. So we can scratch off this one, and we can scratch off this one. And electronegativity blanks from top to bottom. From top to bottom, it decreases. So looks like this one. Let's also type out from left to right. It is effective nuclear charge. It causes the change within a period. From top to bottom, shielding effect, shielding effect versus effect of nuclear charge causes the difference between those two. A non-polar bond will form between 2 blank atoms of blank electronegativities, identical and equal. So if you have 2 chlorines, they would be identical, and their electronegativities would be equal, so the bond would be completely nonpolar. The Lewis dot structure for ASH3 shows blank non-bonding pairs of electrons. There's one pair on the arsenic that is not bonded. The Lewis PF3 shows this neutral atom has pairs again, so 1 non-bonding and 3 bonding pairs. So that's 2 electrons and 6 electrons. 1 that are non-bonding, 3 that are bonding. Lewis dot structure of CHCN. Might need to draw this one, people. Let's see. We have H, little space, C, little space, N. Let's add some dots on there. We'll do those in blue. Let's see. Nitrogen has 5. Let's put the double pair on this side. Carbon has 4. Then hydrogen has 1. And then we bond them. And we bond them. Carbon needs more, so does nitrogen. Bond them. Carbon needs more, so does nitrogen. Bond them. Okay. So we have how many? Nitrogen has blank non-bonding pairs. Nitrogen has 1 non-bonding pair. There it is right there. That's a non-bonding pair of electrons on the nitrogen. Carbon has 4 bonding pairs. Hydrogen has 1 bonding pair. Alright, use the table average bond energies below to calculate a delta blah blah blah. So this is the bond's broken side, this is the bond's formed side. So every one of these bonds needs to be broken, and every one of these bonds needs to be formed. So this side is the positive side, and this side's the negative side, meaning we put in positive, we put in energy, crack, 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 break them apart, and then energy is released, boing, 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 released from this side. Those sound effects are really key. Boing, 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 crack, 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 crack. So let's see, what do we have? We have 2 of these, we have 2 of these, so this times 2. We have a triple bond, so just 1 of these. We have an HI, oh, but we have 2 of those. So 2 times this plus 2 times that plus 1 of those. Write that down. 2 of these, 2 of these, 1 of those. That represents all of this side. On the other side of the reaction, I'm going to switch to red. The CH occurs 4 times. CH occurs 4 times, but now it is negative because we're making it, so it's releasing that energy. The CI occurs twice, so I'll multiply that by 2. And again, it's negative because we're making it, releasing that energy. And the CC occurs just once. I'm going to put a -1 there. So now we need to add all those up, and I need a calculator. Alright, so I grabbed a calculator, and again I'm doing 839 plus 2 times 299 plus 2 times 413 for all of the bonds I'm breaking over here. Change that to brown. For all of these bonds I'm breaking, change that to brown. For all of the bonds I'm breaking over here. And then for the product side I have negative 348, negative 2 times 240, negative 4 times 413. And the answer is negative 217. That is an exothermic reaction because there's more energy released, negative 217, negative, negative, negative release, than energy put in, exothermic. Same thing's occurring in number 21. So again, I'm going to do this side minus that side, and the answer ends up being negative 116. Most people forget that this is CH3, so this CH value is times 3. There's a CO, then there's an OH. They also forget that there's 2 hydrogens, so you got to do H2 times 2. And there's only 1 CO. I don't have my textbook with me. I don't know the answer to this, and I don't have enough information on my previous 2 pages because there's no bromine. But you look up the values, and again, you do this side, break them apart. This requires energy. You gotta break all those bonds, slice them up, 1, 2, 3, 4, 5, 6 bonds being broken, and that would be the positive side. And then as these were formed, that would be the negative side. Which of these molecules would be the shortest in distance? Carbon to carbon distance, shortest. It's definitely this one. We have the triple bond, so those 2 elements have to be close enough together to actually bond to each other. That is the triple bond. Let's see. Chlorine's the most electronegative. Least electronegative of this bunch would be rubidium. Which one of these is the least polar? Not this one. That one's ionic. It's not this one. This one's ionic. Let's C and F are 3 elements wide. 3 elements away. P and S. Oh, it's definitely that one. They're side by side. Arrange these in order of increasing polarity. Ew. Oh, they're all fluorine and another element. So fluorine is close to oxygen, and then nitrogen, and then beryllium, and then magnesium. Yeah, it's B. It's B. So oxygen and fluorine are right beside each other, so that wouldn't be terribly polar. Magnesium and fluorine are drastically far apart. That would be ionic. The others fit in between. The Lewis dot structure for N2H2. Let's draw N, H, H. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2. Bond, 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 bond. Shows nitrogen with a triple bond. Nope. Each nitrogen has 1 non-bonding pair of electrons. Yeah. Each hydrogen has 1 non-bonding pair of electrons. No. Nitrogen single bond. No, that's double. A nitrogen has 2 non-bond each nitrogen. Now it's C. It's kind of a goofy question. Each nitrogen has 1 non-bonding electron pair. This is a pair, and they are not in the bonding. That's why it says binding versus bonding. Which one of these is the right drawing? It's a D. For resonance for a molecule, all the resonance structures are observed in various proportions. So if you have multiple correct answers, all of the correct answers probably exist, just at different percentages. Which of the following can accommodate more than an octet? Cannot. Oh, okay, cannot. I was going to say. Helps if you read all the words. It clearly says cannot right there, right? So oxygen cannot. Why can it not? Oxygen is a 2s, 2p. There is no such thing as the 2d. There's nowhere for the electrons to spread. So it can't do more than 8 electrons. Which atom can accommodate an octet of electrons but doesn't necessarily have to accommodate an octet? Boron. Boron usually has 6, but there is boron minus 1, which can then do 8. The others 8, 8, 8, 2, but boron can be 8 or 6. Answer 38 is D. The single bonded C to the N would be the weakest and also the longest. When you add multiple bonds, the distance between the atoms gets shorter. So the triple bond, the triple bond is the shortest, single bond is the longest, triple bond is the strongest, single bond is the weakest. So D is true. Double bond is longer than a triple bond. It is not stronger, not stronger, not stronger, not longer. The double bond is longer than. So if you have two elements, single bond, double bond, and with a triple bond, it really pulls the two elements close together, and they're held more tightly. Single bonds are easier to break. Single bonds are easier to break than triple bonds. Is that really all the homework? Wow, that was way too easy. All right, stopping this for now.